Okay, guys, this problem is a bit of a doozy. It may seem straightforward at first, but it does ask you to use a couple of skills that may be a little rusty for you. So not only do you have to use the Rydberg formula, but your algebra has to be pretty good in solving for a variable. And you also have to have a conceptual understanding of what's going on in the problem. It says an electron in a hydrogen atom is in the n equals 2 quantum state, and it absorbs a photon with a wavelength of 656.3 nanometers. It's asking you to calculate the final quantum state. So the conceptual part that you have to be able to say to yourself first is that the electron absorbed energy. So since the electron absorbs the photon, it went from a low energy state to a high energy state. Now, I know that this says the photon absorbed energy. I'll go back and change it at the end of the solution. It's really the electron that's absorbing energy. But what that means is that it goes from an n equals 2 quantum state to some other quantum state. And what do we know about that quantum state? Is that it's a higher quantum level. Since we know that it's a higher quantum level, we can correctly write down the Rydberg formula. And remember that the factor in parentheses involves the lower quantum level subtracted from the higher quantum level. And so this way we can correctly set it up such that when I change my wavelength to meters, I know that it's 1 over 2 squared minus 1 over the variable x is what I'm going to call it that I'm solving for. So now I put everything together. And so let's go ahead and start to simplify the equation so we can do the solution. So I'm going to rewrite the left side, and I'm going to go ahead and put in the Rydberg constant, 1.097 times 10 to the 7th per meter. And it's 1/4 over 1 over x squared. Now I can start to solve. The first thing I'm going to do is divide 1 by the wavelength. So 1 divided by 6.563 times 10 to the negative 7th meters. I can just do that in my calculator, and I get 1.524 times 10 to the 6th. And it's still meters in the denominator, so that's meters to the negative 1. So I'm going to write everything else down, and I still have everything exactly the same on the right side. Now what I can do is I can divide both sides by 1.097 times 10 to the 7th meters to the minus 1 to start isolating the variable. So on the left-hand side, I get 1.389 times 10 to the negative 1. And now notice that the units are gone. If you take meters to the minus 1 and you divide it by meters to the minus 1, they cancel. So you end up with something that's unitless. And that's what you want because the quantum level does not have a unit. And so I end up with 1/4 minus 1 over x squared. Now I'm going to subtract 1/4 from both sides, and I get negative 0.1111078 equals negative 1 over x squared. Now, I've got a negative on both the left side and on the right side, so I can go ahead and cancel that or divide them both by negative 1 or multiply them both by negative 1. Either way you want to look at it. Anyway, it becomes positive. So I get 0.11078 equals 1 over x squared. Now, it's 1 over x squared, so I need to take the inverse of both sides in order to get x squared in the numerator. So if I take 1 and I divide it by 0.111078, I get 9.003, and that equals x squared. And so taking the square root of both sides, I get x equals 3. And now remember, the quantum level is a whole number. So even if you get 2.999 or 3.0001, you need to understand that as a whole number. The reason that you don't come up with an exact whole number in your calculator is just rounding errors. And so the next conceptual bit that you need to have is that it's a whole number. And then let's go back over here. Let's change this. The photon didn't absorb the energy. The electron absorbed the energy. Okay, guys, that's it.